All right, welcome to our fifth video of our Unit 5 Graham's Law. This is honors only, so if you're general and watching this, don't worry about it. But for honors, well, let's get started. So, to begin with, gas particles move around at constant, rapid, random motion, especially when, given space to do so. They always are moving. That's the thing you got to realize. And they're always moving in basically a random motion. So, you got that covered. Gases move. All right. Diffusion is the movement of particles from higher density to regions of lower density, but, if there's plenty of space. Diffusion is why gases spread out. Like if you spray perfume somewhere, given time, everyone in the room will smell it. Maybe not that much, but there's a high concentration where you spread it, where you spray it, and then everywhere else is lower, so it'll slowly spread to that area. Okay? Effusion is when gases diffuse through a tiny opening. So diffusion is going from this to this, taking up more space. And effusion is like if I've got a balloon, I'm going to pop a hole here, it's the gases coming out of that tiny hole. So, diffusion, effusion. So, Graham's law of diffusion, or effusion, states that at constant temperature and pressure, the rate of effusion of a gas is inversely proportional to the square root of the gas's molar mass. Okay? That means that as the molar mass of a gas increases, it will effuse slower. Let me say that again. As the molar mass of a gas increases, it will move slower. Now that should make sense, that bigger gases move slower. Okay? Not to be kind of crude, but think of people that you typically know that are really big people. Okay? Typically, you don't think of people who are rather overweight as running marathons. They don't move that much. It takes a while to move. Now, again, sorry, bad example. Obesity is a serious issue. I'm not trying to make light of that. But it's just bigger things are harder to move. And bigger gas molecules, while relatively tiny to us, do move slower than smaller gas molecules. So, in equation form, this is, this. Okay? Ultimately, we use this to compare two different gases. So A and B are two different gases. And you can see that the rate of A is equal to basically, you've got rate of A on top, but its molar mass is on bottom. That says as A gets bigger, it's going to go smaller. B is on bottom, but its molar mass is on top, and they're all square rooted. So, first off, try to memorize this equation as soon as you can. It's not hard. Just remember that, A is on top and then on bottom. Basically, they're cross. It's not both A's on top or both A's on bottom. Okay? And again, A and B just represent two gases you're comparing. All right. So first off, which gas will effuse faster, hydrogen or fluorine? And B, how much faster will the faster one effuse? Now, I'm going to let you work on that for a bit. The first one's not that hard. You got this. The second one, you are going to need that equation I just showed you. So try it a bit, come back, and I'll show you what to do with it. All right, so welcome back. To begin with, H2 has a molar mass of 2.02, and F2 has a molar mass of 38. Well, your first question is which one's smaller? And that's H2. That means that H2 will effuse faster. Now the second one says, well, how much faster? All right, so here's what we're going to do. We're going to take our rate of H2, and we're going to divide it by our rate of F2. So, and that, then will equal our molar mass of F2 over molar mass of H2. When set up like this, whatever answer this ends up getting will tell us how much faster the top one is over the bottom. I'll say that again. This equation is set up so that the answer to get received from the right side of the equation tells you how much faster the top gas on the left is compared to the bottom. meaning if that number is greater than 1, the top one's faster. If that number is less than 1, the bottom one's actually faster. But it's designed to tell you how much faster the top is over the bottom. So, let's plug our numbers in. That'll get us 38 over 2.02, which in your calculator gets you 4.34. That says that our top gas is 4.34 times as fast as our bottom gas, which means that H2 is 4.34 times faster. Now, what its speed is, I don't care. But, for example, if fluorine was 10 meters per second, then hydrogen is 43 meters per second. That's basically what we're saying. But that's all you do. So, there you go. All right, so at room temperature, gas A has an average speed of 300 meters per second, while gas B has an average speed of 200 meters per second. How do their molar masses compare? So we're going back to that equation, and by that I mean you're going to go back to that equation, try it for 3 minutes, come back, let me know what you think. So, have fun. All right, so we've got our rate 1, actually rate of A over rate of B equals molar mass of B over molar mass of A. All right, so while the right side will tell us how much faster A is compared to B, the left side will tell you how much bigger B is than A. So I'll say that again. The right side will tell us how much bigger, faster A is compared to B. The left side tells us how much bigger B is compared to A. So, plug in our numbers, solve it. I'll show you what we do with that. Those numbers they gave you up there are our rates. So we have 300 over 200 equals the square root of B over A. Okay, so that gets you 1.5. Then I'm going to square that so that we just have our B compared to A. All right, you square that, you get 2.25, and that says that our compound B is 2.25 times larger than our compound A. So B is 2.25 times basically heavier than A. And that's your answer. Just using the same equation. But there you go. Our last example. I'm going to let you try this one again. Still using that same equation. You got this. Spend a few minutes. Come back. All right. So we're looking for the molar mass of a gas if it diffuses 16 times faster than oxygen. So we're not just comparing. We're actually finding, a final answer. So what we're going to do is if something diffuses 16 times faster than oxygen. Well, let me show you this again, actually. So we got A over B equals B over A. Okay, so the answer of this tells us how much faster A is than B. Okay, so if I have a gas that is 16 times faster than oxygen, then that means I want to set it up like this, where I've got the rate of I'm going to leave A to be my unknown, over oxygen equals my square root of, my molar mass of oxygen over A. Because I know it's 16 times faster, that means that 16 is equal to the square root of those numbers filled in, which I've got 32 over A. So it's 16 times faster, and this is set up to tell us how much faster A is compared to B. So that means that if we put our unknown on top, then our left side just turns into 16. Molar mass of oxygen ends up being O2. So you square that, do a little bit of math, and you'll get that our molar mass of A, is, oddly, 0.125. Now I'll admit, I think I actually made this example, and I'm guessing I didn't quite make a good example, because that's stinking tiny. But if it is 16 times faster in auction, it's got to be a crazy tiny gas. So right now, I'm not sure what went wrong. I've done this a few times. So we got 0.125. You used it properly. It's just a weird problem. But that sums up Graham's Law. I know it is a bit hard. This is probably the hardest in the unit, to be honest. But yeah, that's Graham's Law.